So let's do the pH. Let's find the pH for weak bases. First, let's look at our Appendix D so we can see what those equilibrium constants are. So first, here are the Kas for the acids, and here are the Kbs on the next page. So I'm going to write all over this. So for a strong base, you don't need to use Kbs because you just take the log of the hydroxide ion. I'll show you that later. For the bases, you have ammonia here, and ammonia has this Lewis structure. When you add H plus to that, the H's will go on top of the NH3 on those lone pairs and become NH4 plus. So you can see this, that's ammonia. Okay, let's look at that. Notice that all of these have nitrogens as well. This is aniline, and I drew it like this. So you can see that the H plus can go there. Okay, so there's a C6H5 is this ring. Each corner is a carbon, and then there's the N, and then the two H's. Okay, and here is dimethyl amine right here. Notice that there are two CH3s and one H. The N is in the middle, two CH3s, and one of them is an H. I'm sorry, this should be an H. Okay, so the H, the new H plus goes in on top there. And if you notice all of them, they all have the N where the H plus can go on. So that the N is the basic part of this molecule. So when you add the H here, it'll go on top of there. There's the N, there are two dots there. Here you can have two H's. Can go on there, there, and so on. So when this becomes protonated, you put the H after the N, okay? So this becomes NH3, this becomes NH3, this becomes NH3, this becomes NH3, and so on. Okay, so those are the Kbs. So for strong bases, if you have sodium hydroxide, for example, and remember the strong bases are group 1 hydroxide and group 2 Serbaca, strontium, barium, and calcium hydroxides. Okay, so if you have sodium hydroxide, it dissociates 100% of the time. You're going to get 0.1 molar of this, 0.1 molar of this. To get the POH, you just log this number. Okay, easy. But if you have a weak base, you have to use the Kb expression. Okay, so how do bases react when they go in with water? So here I'm going to have to add water to this, and the H, this is water right here, HOH. The H from the water will protonate the lone pair of the ammonia. So now you're going to have NH4. And now, because you added a proton, it'll be a +1. What's left behind is the hydroxide ion, which causes your solution to be basic. So bases react with water to produce the hydroxide. Okay, so the Kb for this reaction is equal to products, NH4 plus, times the other product, over the reactant, NH3. And we don't include water because it's liquid. The concentration does not change. So as you notice, the product always has one more positive than the original, okay? And you always have OH with it, and then the reactant will be the original, okay? So here is the same thing. This is for weak bases, NH3 with water, and so on. These two are conjugate pairs, NH3 and NH4 are conjugate pairs. In between these pairs, this is the conjugate acid because it has the extra H, and this is the base. Remember, conjugate pairs are different by one H. Okay, here again, these two. This water is the acid, conjugate acid. This is the conjugate base. Okay, so the equilibrium constant expression for a basis would be, it's always this substance. So whatever it's H with whatever the base is. So this base can change. and it's always one more positive than the base, which is the original. So it's the base with the H on it, one more positive, and you'll always get OH minus, and base is the original. Okay, Kb is called the base dissociation constant, and you use it this exact same way as you use Ka. Okay, so let's do this. Calculate the concentration of a hydroxide in a 0.15 molar NH3. The first thing you do is write the equation, NH3 plus water. Remember, the H plus goes on the NH3 to make NH4 plus hydroxide. You write the original concentration here. You don't have to worry about this one. 0, 0, minus X, plus X, plus X. So it'll be 0.15 minus X, and X, and X. Okay, if you were able to solve for X, you'll know the hydroxide ion concentration, and you can get the pOH of that, and you can get the pH of the solution. Okay, they just want the OH minus concentration here. Okay, so let us find the Kb using Appendix D. Kb for ammonia is 1.8 E negative 5. So we write that down. Okay, so Kb is equal to ammonium ion times the hydroxide ion over ammonia original. Plugging in the numbers, we get 1.8 E negative 5. We have the X for the ammonium and the X for the hydroxide, so this will be X squared over, we're going to call this negligible for now. We will verify later, so 0.15. Okay, go ahead and solve for X. 1.6 E negative 3. Okay, so this number means that this is how much OH minus dissociated, and that is the question. We'll calculate the OH minus concentration. If they wanted to get the pH or the pOH, just log that number, and you get pOH, and then subtract it from 14. Okay. Next, if we use an assumption here, so therefore we have to check for percent ionization, is equal to 1.6 E negative 3, because that is how much dissociated right here as a part of the intact molecule, 0.15 times 100 is equal to 1%, which means it's less than 5%. We don't have to use the quadratic. So you saw that that's how you do weak bases. We have another type of weak base. Okay, basically there are two types. The ones that we've been doing are nitrogen based, and they're neutral. You see it here, 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 and here. The H goes on top here, here, and here, and there. Okay. There are some that are negative. Okay. All you need basically are lone pairs. So an H can sit there and make this neutral. Okay. So it goes from negative to 0. This goes from 0 to +1, 0 + 1. Remember, you're adding a proton, so it becomes, in the original was 0, add a proton, it becomes +1. Okay, here you have the original is 0, you add a proton, it becomes +1. The Kb is written right here. Okay, the same thing for all of these. Top. Okay, remember when you add the H, for this one, for example, you're adding the H on the N. So the 2 becomes a 3, and it becomes +1. Okay, so these are neutral, but there are lone pairs there. So one H, you can put it in this lone pair right here. So then it used to be minus, you add an H to it, H plus, now it becomes neutral. Okay, H2S, so it becomes a negative. You add a +1 proton, H2S, now it's 0 charge. Again, the H plus came from the H2O, so now you have OH minus, so that is also a base. Okay, and here's some more bases. That's the carbonate ion. You can put the H on one of these right here to make the bicarbonate, which is sodium, baking soda, sodium bicarbonate. And it looks like this. It used to be -2. You add an H, now it's -1. And now you have your OH. Okay, this can potentially take another H, all right, to make it now neutral. Okay, this one can take the H also here on top of there, and you're going to get HClO. Okay, so that is your base as well. Okay, so you can have neutral bases. You can also have anions of weak bases. Okay, so what that means is when ClO minus, which is this substance right here, dissolves in water, it can accept the H plus. When ClO minus goes into water, it can accept an H plus in one of the lone pairs right here and become HClO. You might be wondering, why did they not put the H in front of the O? That's just because to make, we just put it in the front to make sure that you know that's the acidic proton there. Okay, so the H goes from water to that, and now you have HClO and then OH minus. Okay, also this right here, anion, the way we buy that from the store is we buy it as a salt, and it's going to come in a jar, and it's solid. It comes in a salt form. So you just add something positive to it, ClO minus, and you sell it as a solid crystal, where you have a +1, -1, and if you were to zoom in, it looks like a ionic solid. That looks like this, Na +1, ClO -1. Okay, so if they tell you sodium hypochlorite, you don't care about the sodium, you only care about the chlorite, the hypochlorite, which will take the H from the water. Okay, so here's an example. So you have a solution is made by adding sodium hypochlorite, NaClO, to enough water to make 2-liter solution at a pH of this. So NaClO, don't care about the Na, just care about the ClO minus. So you're taking the ClO minus is going to be your base, and you're adding that to water. And you make, the H goes this way, you're going to make HClO and the OH minus. So that is your equation. Okay, so once you write the equation, it says a solution was made by adding solid sodium hypochlorite, so they added this to enough water to make 2 liters. And you have a pH of 10.50. So that means POH would be 14 minus 10.50, which is 3.50. So if you go 10 to the -3.50, you're going to get the amount of OH minus. So this is 3.2 E -4. This is the molarity of OH minus. Okay, so what happened is in the beaker, they told you how much OH minus you have here. So it's 3.2 E -4. Again, I just did 10 to the -3.50 to get that. Okay, once you know that, you know what X is. So that means this is also 3.2 E -4. In the beginning, you don't have any of these two. And they said that you only have sodium hypochlorite, so you have a certain amount of this that you don't know. They're asking you how much of that did you add. Okay, so this is going to be minus X, and this is going to be, we'll call this Y. Okay, so it's Y minus 3.2 E -4. Okay, so what they're asking here is how many moles of NaClO did you add? So they're pretty much asking how much of this did you add? Okay, so just solving for Y, you have your equilibrium expression, which is Kb is equal to HClO OH minus over ClO minus. So Kb of this is written up here, 3.3 E negative 7. So it'll be 3.3 E negative 7 is equal to 3.2 E negative 4. And you have two of them, so you have to square that, divided by y minus 3.2 E negative 4. Solve for y, and you're going to get 0.303. Okay, so that number is the molarity of ClO minus. Okay, so because for every 1 mole of ClO minus, you have 1 mole of NaClO, this is going to be the same 0.303 molar NaClO. The moles here just cancel, and it's still 1-to-1, so you still have the same number of NaClO. Okay, so that means once you have ClO minus, you also have NaClO. Okay, so I'm going to move up here because there's no room. So 0.303 equals to molarity, which is equal to moles over liters, okay, of NaClO. They're asking for moles, and you use 2 liters, so you're going to multiply this by 2 liters, and you're going to get 0.606 moles of NaClO. So, what this means is if you put this much NaClO that you get from a jar of solid and you weigh it on a scale, and you add some water to it, up to 2 liters total solution, your solution will have a pOH of 3.50 or you're going to have a pH of 10.50. That's how you make a 10.50 pH solution using NaClO.